One. Okay, I guess it's time to start. My name is Jaroslav Tulach. I work for Oracle Labs in Prague, and I'm here to talk about languages. So first question for you, what is your favorite language? Anyone? Java, Scala, Clojure, Haskell. Anything else? C Sharp, perfect. I have a slide about C Sharp. C++, perfect. I have a slide about C. My plus plus, almost. For us, just this one. but I have a demo for Ruby and maybe some other languages as well. Okay, let's start. Long time ago, in the last century, I started to work with Java and actually was the initial architect of NetBeans. And I like to say that when designing NetBeans, I made so many design mistakes that I felt obligated to write a book about that. So in 2008, I published Practical API Design Book, which contains everything you would ever want to know about designing APIs, especially APIs in Java. Based on that, I got popular. For example, Oracle Labs noticed me, and a year ago, they convinced me to join Oracle Labs to help to design APIs for Truffle, hopefully this time without repeating all the mistakes I did before. So I have a few slides and an agenda, but I'd like to go through that as quickly as possible. So I will just skim through the slides, and if you feel you have a question, you can stop me. But hopefully we will be able to get to demo, which is the most interesting part every time, as quickly as possible. Okay, so this slide basically says that in Oracle Labs there are some scientists, but also engineers. I'm probably the engineer. Our goal is to release a product, and we do compilers. The compilers look something like this. And actually, it's a Java compiler or a bytecode compiler that is an alternative to HotSpot C2 compiler. So basically, if you are using Java and you are not satisfied with the speed, you may want to consider using the Graal compiler because you can gain some speed. But the real thing that I'd like to talk about is dynamic languages, not only just Java, but dynamic languages. And here, the slides illustrates what it takes to write interpreter or executing environment for your own new language. And it's usually pretty painful because once you finish the interpreter, which is usually the first and natural start, people start to use it and say, yes, that's a great language, but it's slow. So then you probably design some artificial bytecode, convert the source code into bytecode, and the speed speeds up. You give it to people and they say, yes, it's still great. It's better, but it's still slow. So then the option that you have is to probably write a JIT compiler and do basically something like Google did for JavaScript with V8 virtual machine. But the truth is that writing a JIT compiler is usually quite scientific task. And even for Google, it took a few years in a team of tens of engineers. And if your language, if your petty language that you designed can survive such a long, you are in a completely different position. It's no longer a toy language or a language for research. It's a heavy industrial language. And honestly, not many languages get into this state. So we would like to offer a better alternative. The alternative is called Truffle, and that's an API which allows you to write AST interpreters, basically compose the trees of nodes and then execute them by visiting them. And yeah, that's the API that I currently maintain. And our vision is you write the interpreter, you give it to people, they start to use it, and it is already fast. And we hope we basically can create a system like this that would allow any one of you to basically, in a matter of few weeks, create an interpreter for any language that will be reasonably fast. So here is some description of languages that we are considering or trying to target. Here's the C# slide. And actually, yeah, one comment to this slide is that the more statically typed the languages are, the faster they usually are. But once I heard a comment that these days, when more and more people is trying to program, then actually the classical statically typed languages are actually domain-specific languages. They are domain-specific languages for people who do coding for a living, who are interested in types, who want to maintain their application for a long time, and they care about the code base. While currently, the scientists that are using programming languages to dig data, they don't care about the code, they care about the data. They care about fast way to process the data into something useful. And then they are ready to use languages like Python, R, and those languages are inherently slow, at least at their current implementations. And we would like to change that. Okay, so this is a graph showing the comparative speed of various language implementations. And some are slower. Some dynamic languages could get already fast, for example, JavaScript. But our goal is to actually improve the situation and make all the languages almost as fast as the fastest alternative. Yep. Okay, so that's the goal. All languages up to 5 times slower than the fastest one. Of course, and here is another slide about C#. Some might say that we already have JVM and we have a common language runtime, and those allow us to put the languages in any kind of languages and actually make them run reasonably fast, which is true only if the language looks like Java or C#. For example, Scala managed to do that successfully. But if you have different languages, if you have languages like JavaScript, Ruby, R, the semantics is totally different, and like transpiling that into Java bytecode is not easy at all. So we offer you a better alternative. Here is description of how we do it, but let's skip it. Oh, this is the important slide that I need to show because I'm Oracle employee, and if you, based on my talk, decide to buy Oracle stocks, you cannot blame Oracle if it doesn't go up. And yeah, possibly everything I'm talking here about is a fake. So don't trust it, verify it, and only then make your investment decision. And here we finally have the demo slide. Hi. Hello, hello. Can I get this mic? One, no?
Try what happens if you push a button on.
It's push. Hello? Hello? Okay. So, let's start with Ruby, because that's a really nice showcase showing what our technology can do. So here I have a sieve of Eratosthenes written in Ruby. Ruby, sieve, Ruby. Okay, that's the file and font size. Okay. but let's switch to an ID. So Thief of Eratosthenes here is actually this is not a single program in Ruby. These are two programs in Ruby. My first and last one, at least I hope. Um, so this is an iterator for the natural numbers from 2 to infinity. Here is a filter which remembers a prime number and can filter it out if filter some number out if it's divisible by the prime number, and then it has a chain of these filters. And here is the main loop, which takes next number from the infinite list, and if the filter is filtering it, then it's not a prime number, otherwise it's a prime number and we can return it. And here is a computation which computes 10,000, 100,000 of prime numbers and prints the time. And the computation is repeated once again, over again, because, and I forgot to mention yet, the thing that we are interested in is long-running processes, really peak performance. So we really need the system to stabilize. So that's the reason I'm repeating the computation. Okay, now let's run it. I have Ruby installed on my Ubuntu. So as you can see, it starts fast, and it achieves a really nice result of 2.3 seconds to compute 100,000 prime numbers. Well, Ruby is known to be a very slow language. So what we can do, what we are offering is called GraalVM, which is a slightly modified Java virtual machine. Okay, I can show it here. So this is the directory where I have it installed, and it should look similar. If you know how the layout of Java virtual machine looks like, it really should be similar. So all the essential utilities are present. But in addition to that, we also have a utility called Ruby, which is our Ruby interpreter. So I will run the same program with Ruby, with our interpreter. And as I wanted to warn you, the warm-up is not that fast, but once the application starts running, it can actually achieve relatively good results. And as I said, we start with interpreters. So right now, the system was interpreting, but now the GraalVM really compiled the tree of the AST tree and compiled it into native code. And the result is relatively good. So when I was, a year ago, when I was joining Oracle Labs, my future colleagues claimed that they can run Ruby 10 times faster than any other implementation. I said, well, yes, oh, sure you can on some benchmark. I will test it. So I wrote this program, the Thief of Eratosthenes, and really, yeah, the result is something like almost 15 or 20 times faster. So yes, the system has some potential. Now, of course, these days, nobody wants to write in Ruby. Am I wrong? Anyone, any Ruby fan around? No? Yeah, of course. But it's good showcase. So these days, everybody writes in JavaScript, right? So what I did is I rewrote the whole program into JavaScript. And again, we have the natural numbers generator, we have the filter, which can filter out the prime numbers. Then we have the major loop in prime numbers, which takes next number and checks whether it's divisible or not. And if not, it adds it as a next filter. And then the main loop, which actually computes those 100,000 prime numbers and measures the time. Let's switch back. And of course, if we want to compare with something, then the best thing is to compare with V8. So I have Node installed on my computer. So let's run the computation in Node.js. And, well, it starts faster, but as you can see, it actually needs even slightly more time than our Ruby implementation to compute this algorithm, which is probably caused by the fact that I don't have the most recent version of V8. They are working on improvements, and probably they can be better now. Anyway, let's see how our implementation of JavaScript can deal with that. So again, we have JS. Inside of the Graal virtual machine layout, there is a JS command which launches our JavaScript interpreter. And it's surprisingly fast these days. So first round, again, slower. But now it starts to optimize, and yeah, we are below 100 milliseconds. So what does this mean? Does this mean that we have to rewrite all our software to JavaScript? Um, well, some people would like to believe so, but actually we think we have a better idea. Let's rewrite just the critical parts of our systems to JavaScript. So here, I will close this. So here I have basically implementation which is mixing Ruby and JavaScript. So the Ruby still has the generator of natural numbers. And what it does, it uses something like interoperability API, which is defined by this truffle system, and it exports the method which generates the infinite list under the name natural. And in the JavaScript version, I actually removed the natural number generator, and instead of that, somewhere here down below, I actually used the interop here. I used the interop to find out the natural symbol exported by some other language. I don't necessarily need to know. Okay, so let's try to run this. And here, actually, I don't have anything to compare to, because there is no other system on the planet that would run Ruby and JavaScript at full speed and allow exchanging of the objects in memory. So for that, we have a special utility which is called GraalVM, and it allows me to pass in the scripts that I want to execute. So first of all, I should execute Ruby to export the natural symbol, and then I will use the JavaScript. Is it correct? Hopefully. So now, after the initialization period, the system actually runs and mixes Ruby and mixes JavaScript. And again, it needs to do some optimizations, but then, yeah, it's actually faster. It's maybe the fastest running system right now. So it's certainly faster than Ruby. So by rewriting some part of the application to JavaScript, we can actually improve the speed, but we can keep the, I don't know, business logic or the core of the algorithm. So we don't need to rewrite all our applications to JavaScript. But of course, some of you said that you like Java. So now the question comes, can we also mix this system with Java? And yes, we can, Ruby and JavaScript. So here is an example, and it shows the Truffle API that I'm responsible for. So it starts by creating a Polyglot engine, which is basically an isolated execution environment, which allows us to execute scripts. And you can have as many instances of such engines in the VM as you want, and they all should be isolated. Then it locates the source files that I showed you before, this one and this one. And it creates a source object for those files, and first of all evaluates Ruby, and then it evaluates JavaScript. So let's try to run it. And you can see it's Maven project. So nothing fancy. It sets up the virtual machine with the scripts, and after a while, it should run. And of course, the speed of this should be the same as in case of the previous example. But the advantage here is that you can basically use this system to embed any Truffle language into your program, and it will really run at full speed. And you can communicate with those languages through Java. We have Java Interop API. So I hope I convince you that Truffle and Graal can give you a speed, give your language speed. However, that's not all. The other thing that we can give you is tooling. Actually, uh, on the first slide, or on the slide with the languages, when I compared the complexity of creating a language, I probably forgot to mention that one of the most boring tasks is to write a debugger. I created few languages in past myself, and none of them has a debugger. I always resort to printing out some output statements and do debugging by logging because it's easier than to try to spend time on creating a real debugger. However, with Truffle, you don't have to spend any time on creating a debugger. We will give you debugger for free. So let's try to run it. So I will start the application in debugger, and that's normal Java debugger, JPDA. We connect to the Java virtual machine. Here we can see the threads. And yeah, it should do the initialization and stop here before evaluating the JavaScript. Okay, we are here, and I will step into. And now, what shall happen is that actually the system will find out that right now I'm evaluating JavaScript and will show me the JavaScript source code. And if I step over, I really the system really steps at the right locations of the program and can understand JavaScript. And actually, in the debugger, which is integrated with NetBeans, there is nothing JavaScript specific. It only knows about the Truffle APIs, and based on them, it can debug any language. So I will continue, and yes, okay, here we are. We hit a breakpoint, and you can see that we even understand the values. So what values are on stack, what is the structure of these values. So all of this can be extracted from the languages in completely language agnostic way. But now, here is, remember, we have the mixed application. Part of it is written in JavaScript, part of it is written in Ruby. So right now, this natural object is actually, it's external object. So that means it's unknown to JavaScript. I will step into, and here we are in Ruby. And now you can really see that the IDE does not understand Ruby at all, because it doesn't even syntax coloring, it has nothing. Yet still, it can debug it. And if I return back, okay, I'm back in JavaScript, and I actually really can see the value returned from the Ruby, which is integer. I see the stack, which is transferred to look like the stack you would expect from the scripting languages. And all of this is basically for free. So, before I go on, don't you have a question? Okay, here is a question.
What's your bytecode like?
What is our bytecode like?
Yes, intermediate
We
language.
don't
whatever.
have any bytecode.
So you just customize. You have a custom.
So the thing is that we really write interpreter. So we have, of course, the language. When you code the language, we have I don't know, JavaScript assign variable node, JavaScript read parameter node, and so on. So these classes have bytecode, but unlike Nashorn, which basically takes JavaScript and converts it into bytecode, we don't do that. We stop on the level of interpreter, and if the interpreter is written correctly, then you get the speed even without generating the bytecode. Thanks.
So I'm wondering about some of the. You're saying that we can use a common VM for different languages. I'm wondering about some of the language-specific things you would find in a VM, like support for a language-specific ways of laying out objects or for tail calls.
Yes, okay, so the question is what to do with the tough concepts that the Java virtual machine does not support at all. So, it's slightly more detailed question that I was prepared to answer, but I at least, okay, I know what to do with variable access. Well, probably I should return back to slides then. So I will get to answer to your questions soon. Okay. Oops, that's not the slide. This is the slide, and go back. So actually, this is the slide explaining how we do it. So in the box on the top, you see the most complicated expression in a dynamic language, A plus B. And the reason why it's complicated is that we don't know the type of A and we don't know the type of B. And the A and B can be anything. It can be integer, it can be string, object, and actually they can be of different type. A and B can be different. And of course, handling all these cases puts heavy load on, well, complicates the interpreter. And of course, if you just blindly generate the native code with all these checks, it won't be fast. So what we do? So when you parse your source file, you create the tree of the nodes, of AST nodes, and they are in so-called uninitialized state. So we know they represent the structure of the program, but we don't know which data are going to flow through this location in the program. And each language, and this is partially answering your question, so each language can define their own table of types. So those types can be Java specific, like string or integer or double, but for example, Ruby has something like big integer, but a special big integer, not the Java one. And they can also include that into the transition table. And the transition table basically says, okay, if at a certain location in the program arrives data of type integer, then switch to the blue state. If then arrives data of float data, then switch to the D state, the double state. If then arrives something with string, then switch to generic state and be slow. But the observation that we made is that most of the time when you write a plus somewhere in your program, it usually, the parameters of that operation are usually fixed, and they don't change that much. So if it operates on numbers, it will operate on numbers most of the time. So these specializations, how we call them, usually work and allow us to color the originally uninitialized tree in a way that we know what data are actually floating through the program, through the user program. And then, if we find out that that part of the tree is executed quite often, the Graal compiler kicks in and compiles that code into native code, which is specialized for dealing with integers in this case. Of course, the natural question is what happens if something else than integer arrives at the input?
I have a question. I'm here.
Okay.
I just wanted to understand a little more. Is the GraalVM forking threads for the native language and caching the results?
No, not at all. It's most of the VM is basically single-threaded. So in the example that I gave, you can call eval, and the eval function just calls into the interpreter, and the interpreter then does something like, okay, to evaluate this node, I need to know the left value, so it calls into the left node to produce the value, it calls into the right node to produce a value, and then it does plus, for example, with those values. So everything is mostly single-threaded. So back to the optimization. In case we find out that the compiled code has assumptions that the values will be of type integer, and suddenly there appears to be a parameter of type double, we de-optimize. We throw away the compiled code, and instead of that, we switch into the interpreter again. And because the interpreter has the transition table that knows how to color the nodes, it will change part of the tree to be more generic, to work, for example, with doubles. And then, if we find out it's used really frequently again, Graal will kick in and compile it into a native code once again. So this is how it works. Your question was what we do with object access. If, for example, we are trying to access some structure of a language which is not common in Java, which has some special semantics. So actually, if we, for example, want to call a function from JavaScript to Ruby, then the JavaScript gets an object, we call it a truffle object, and it finds out that it's some foreign object, knows nothing about it. And the only thing that the JavaScript can do is to send a message, like small talk-like message to the object and ask him, okay, I want to execute you with n parameters. So please give me an AST for doing the execution. And as a result of that, we can end up in a system that if this represents JavaScript, then suddenly below here is a tree mounted, which is actually a tree of nodes from Ruby. And we can actually have a heterogeneous system of nodes coming from really different languages. And they all follow the same rules, like specialization and a way how they are interpreted, basically. But at the end, when the Graal VM sees, or the Graal compiler sees such a tree, it does not differentiate between the nodes coming from JavaScript and the nodes coming from Ruby. For the Graal compiler, everything is a node, and it can optimize across the language boundaries, which was the reason why the mixed program with JavaScript and Ruby was actually even faster than the only Ruby program. Okay, and another question. Let's go on. Can we cache optimizations between runs? I believe when I joined, there was some support for serialization of the nodes. So that would mean that basically the structure after the program was executing for a while, the structure could be dumped out and probably read again next time. But we deprecated that part and remove it. So in case of the Graal VM, basically the open source part, we don't do that. But there is another research project in Oracle Labs called Substrate VM, and it basically does exactly this. It runs the application for a while, let it warm up, and then it can dump the state in which the application is into the executable. So it really starts quite quickly, but that's not open source.
Do cross-language exceptions work in this system?
Cross-language exceptions. There is not much support for that. Basically, we use Java exceptions. So once you throw exception in, oh, I'm sorry. Oops. I'm talking for too long. So basically, the interpreter is completely written in Java. So the semantics are primarily taken from Java. And so if you throw an exception in your language and it's get propagated to another language, it's just like throwing Java exceptions. You probably let them throw or you catch them depending on what you want. There was some request to somehow standardize the exceptions between the languages, but we have not done that yet. But now I remember your question was about tail recursive calls. And no, 5 minutes. Oh, okay. So the Taylor recursive calls are actually handled, or the complete control flow is actually handled by exceptions. So if you, for example, have a node representing a method, which inside of it has another node representing while cycle and another node representing if cycle, and inside of that is a return statement that should return from the whole method, then what we do is we throw a control flow exception, which is something like a return exception, for example, and the exception is caught on the top of the method, and then it returns directly from the call. And the Graal VM is optimized for these kind of control flow exceptions. And the tail calls can probably be simulated with the control flow exceptions as well. So rather than calling a Java method, you first throw exception, and when you pop the stack, you actually do the call. So that means the stack is not polluted with more and more calls. Okay.
Uh, how do you ensure interoperability of types between various languages? You said that Ruby has where begin. So when Ruby returns that Ruby begin to do JavaScript, how can JavaScript handle it?
Again, this is done through messages. So all the languages are supposed to handle the primitive Java types, like all the numbers, string. And if they return something which is more complicated, they return the truffle object. And that's the completely opaque thing. Nobody, and the JavaScript doesn't know what to do with it. It can only send messages. And one of the messages is unbox. So if, for example, JavaScript expects a number at a certain location and gets foreign truffle object, it can ask it to unbox. And if it really represents a number, then the Ruby will handle the conversion into some primitive Java type. So that's how we do it. Okay. So I should probably mention that this is all open source. So if you want to contribute, and we are certainly looking at contributors from the academia, then if you go to GitHub, GraalVM, you will find out a lot of projects. Graal core is exactly the Graal compiler. Truffle is the API for writing the interpreters. And then we also have Ruby and FastR, which is another language that we are trying to implement. Anyone interested in FastR? Anyone? Sorry. Anyone knows what R is? Yeah. Oh, okay. Then I have to do a demo. Because I think I have the similar algorithm for.
Speed diagram again.
I'm sorry.
The diagram of the language speeds.
That was the diagram of current language speed, not with our language speed. So it's not important anymore. Okay, so basically here is the same example using the computing the sieve of Eratosthenes, but this time with R and JavaScript. So let me try to debug it. We'll see how that goes. So once we initialize R, JavaScript is relatively fast in its initialization, but the other language is not that much. So now we are stepping into JavaScript, and I have a feeling that somewhere along the lines there I should have a breakpoint. Okay, we are here, perfect. So again, this is the JavaScript part which does the computation, and yes, here is the interop. And actually the natural symbol this time should be exported from R. So let's run it, stop and the breakpoint, and I will step into. And yes, we can debug even R language. And there is a reason why the R language is called FastR, because we used to have a workload inside of Oracle, one group computing something for pharmaceutical company, and their workload was really slow, mostly written in R, very slow, and they needed to rewrite parts of it into C to make it even fast, and then they were able to finish the computation in something like 2 days. And they got in contact with us, and we tried to run their scripts with FastR. And actually, we throw away the C part. We took the old version, which was completely written in R, and now we are able to finish it in 18 hours. So it should basically show that we can be fast, and that it saves you the time of really rewriting parts of the R, which is nice for prototyping, because with FastR, it's really also fast. Okay, I think I'm out of time. There is a question. I can go.
Can you show C or Sulong or
C or Sulong. I cannot show you Sulong, but I can show you the C implementation. So here is the, one friend of mine, really good friend, asked, and how fast C would run? So I had to rewrite the algorithm in C as well. Yeah, the difference is that I need to do the garbage collection myself of the allocated structures, but otherwise it's the same thing. So I will try to run it, and yeah, of course it starts fast, but the time it needs is 97 milliseconds. So basically, that's even slower than our JavaScript implementation. And of course, what I can show as well is implementation of this in Java. So I have a Maven project, C, algorithm, pom, exec, Java. So this is running on Java, and that's 86 milliseconds, but that's not normal Java, that's the hotspot. But we can also run it on GraalVM, because the GraalVM comes with, wow, no, I lost VM, no, GraalVM, yeah, 2L, yes, GraalVM. Okay, so basically what we do is to change the Graal compiler, or the compiler of bytecode. Then actually we can even speed up Java programs. That's not all the time. Usually we are on par with the system, but when we are lucky, we can actually run in 75 milliseconds compared to those 86 milliseconds the normal production JDK can. And the speed up is even better for if you use some modern constructs of languages not available in 2006, because the major development of hotspot happened something like 10 years ago. So if you run Scala, you can get something like 20% speed up, because we can recognize the classical Scala constructs and really make them run faster than on classical hotspot compiler. There is a question? Yeah.
Do you have a static typing language example?
Java?
Yeah, but except for Java. You talk about
in
Scala.
the languages that we do.
Did you try Scala, for example?
I think there was some experiment with Clojure. Is it not static typing? Ah, okay. I don't know. From the languages that we do the JavaScript, Ruby, and R, and those are part of the download. So if you basically visit our website, if you look for Oracle Technology Network GraalVM, then you get here and you can download all that I demonstrated, and you can, or the VM that I showed, and you can play with it. But there are only those 3 dynamic languages. But there are various implementations of other languages done by universities. Some of them might be typed. I just don't know offhand.
We can do a few more questions because of the coffee break.
So whoever wants to go for coffee, you can leave.
Yeah, but so essentially you evaluating abstract syntax tree, right?
Mm-hmm.
So, but do you think, like in retrospect, like doing bytecode stuff like 20, 30 years ago was a mistake? I mean, like, or was it just like, I mean, why nobody came up with that idea before? Well, I mean, why it happens only 5 years ago or something?
The thing is that there was a tremendous amount of investment in research and development of interpreters of dynamic languages, or of runtimes for dynamic languages.
I just asked you because you probably have more experience.
Well, I mean, especially V8. Basically, Google with V8 JavaScript engine demonstrated that you can be really fast with JavaScript as well. And this is something that in 2006 nobody would predict. And we are talking about 2006. Java was created even 10 years ago. And at that time, it was completely out of mind that something like that could be fast. 20 years? Yeah. So I think the bytecode, actually, when you look at the picture that I showed, how you want to speed up your language, then not having interpreter, but generating a bytecode and emulating the bytecode is a natural way how to speed it up. So I think Java did a relatively good decision. But these days, it shows that even the dynamic languages can get up to the speed of such system.
Anyone else?
If you really want to go to have a coffee, then we can end up.
Or we can finish and we can do all other questions in private. So let's thank the speaker. And
Okay, thank you. That is an alternative to HotSpot C2 compiler. So basically, if you are using Java and you are not satisfied with the speed, you may want to consider using the Graal compiler because you can gain some speed. But the real thing that I'd like to talk about is dynamic languages, not only just Java, but dynamic languages. And here, the slides illustrates what it takes to write interpreter or executing environment for your own new language. And it's usually pretty painful because once you finish the interpreter, which is usually the first and natural start, people start to use it and say, yes, that's a great language, but it's slow. So then you probably design some artificial bytecode, convert the source code into bytecode, and the speed speeds up. You give it to people and they say, yes, it's still great. It's better, but it's still slow. So then the option that you have is to probably write a JIT compiler and do basically something like Google did for JavaScript with V8 virtual machine. But the truth is that writing a JIT compiler is usually quite scientific task. And even for Google, it took a few years in a team of tens of engineers. And if your petty language that you designed, design mistakes, that I felt obligated to write a book about that. So in 2008, I published Practical API Design book, which contains everything you would ever want to know about designing APIs, especially APIs in Java. Based on that, I got popular. For example, Oracle Labs noticed me, and a year ago, they convinced me to join Oracle Labs to help to design APIs for Truffle, hopefully this time without repeating all the mistakes I did before. So I have a few slides and an agenda, but I'd like to go through that as quickly as possible. So I will just skim through the slides, and if you feel you have a question, you can stop me. But hopefully we will be able to get to demo, which is the most interesting part every time, as quickly as possible. Okay, so this slide basically says that in Oracle Labs there are some scientists, but also engineers. I'm probably the engineer. And our goal is to release a product, and we do compilers. The compilers look something like this. And actually, it's a Java compiler or a bytecode compiler. These days, when more and more people is trying to program, then actually the classical type, statically typed languages are actually domain-specific languages. They are domain-specific languages for people who do coding for a living, who are interested in types, who want to maintain their application for a long time, and they care about the code base. While currently, the scientists that are using programming languages to dig data, they don't care about the code, they care about the data. They care about fast way to process the data into something useful. And then they are ready to use languages like Python, R, and those languages are inherently slow, at least at their current implementations. And we would like to change that. Okay, so this is a graph showing the comparative speed of various language implementations. And some are slower, Some dynamic languages could get already fast, for example, JavaScript. But our goal is to actually improve the situation and make all the languages almost as fast as the fastest alternative. Yep. Okay, so that's the goal. All languages up to 5 times slower than the fastest one can survive such a long. You are in a completely different position. It's no longer a toy language or a language for research. It's a heavy industrial language. And honestly, not many languages get into this state. So we would like to offer a better alternative. The alternative is called Truffle, and that's an API which allows you to write AST interpreters, basically compose the trees of nodes and then execute them by visiting them. And yeah, that's the API that I currently maintain. And our vision is you write the interpreter, you give it to people, they start to use it, and it is already fast. And we hope we basically can create a system like this that would allow any one of you to basically, in a matter of few weeks, create an interpreter for any language that will be reasonably fast. So here is some description of languages that we are considering or trying to target. Here's the C# slide. And actually, yeah, one comment to this slide is that the more statically typed the languages are, the faster they usually are. But once I heard a comment that Okay, I guess it's time to start. My name is Jaroslav Tulach. I work for Oracle Labs in Prague, and I'm here to talk about languages. So first question for you, what is your favorite language? Anyone? Java, Scala, Clojure, Haskell. Anything else? C#, perfect. I have a slide about C#. C++, perfect. I have a slide about C. My plus plus, almost. For us? Just this one. But I have a demo for Ruby and maybe some other languages as well. Okay, let's start. Long time ago, in the last century, I started to work with Java and actually was the initial architect of NetBeans. And I like to say that when designing NetBeans, I made so many